Alrighty, welcome back. So in the last video we made a component that was a custom created component. In this video we're going to do a breakout board for that component. So this is a common thing you have to do if you have a weird footprint device that you can't just buy an off-the-shelf adapter for it, but you still want a prototype with it to make a breakout board for it. So one thing we're going to do, one thing I forgot in the last video is, so we left off exactly where we pick up right where we left off before. If we go to the to our schematic library and we go to that part that we created, one thing I forgot to do was make this comment visible. It's sort of an option, right? We always want to have the designator be visible, but the comment here, which is going to show the actual part number for the component, I like to have that visible as well. And what Altium is going to do is it's going to, by default, it's going to put the designator up at the top portion of the symbol, and it's going to put the comment in the bottom underneath it. So, but I think it's nice to have on a schematic where you can actually see not only what the designators are, but also know what parts these actually are. It makes it really easy to look everything up and or sort of note what people are doing. So we're going to make that change, and that's the only thing we're going to do. That we're going to save. So we're going to go back to our so we have completed. We created the PCB library, the schematic library. We did the footprint for our part in the PCB library. We did the schematic symbol for our part in the schematic library, and we linked the two using a pin mapping. And so now what we're going to do is we're going to try to use this part that we just created, and one that's going to test how well we made the part. We're going to use it to create a breakout board for this part. So for the breakout board, I'm going to create a new project. So two-layer PCB project. We'll call it Buck Breakout. And so that created, using the template, it creates automatically a schematic for us and a board file for us. Now we're not going to, in another video I had, we went through sort of how to change the global variables and everything to update these values to make this a really good professional schematic. I'm going to skip that for this video. We're just going to go rush through basically and create what we need for a board. And I think for this one also, I'm going to go through the process of exporting those board components and having those things printed. One thing that was particularly of interest is people were asking about how to make boards for PCB Way, and so we'll talk about that, and maybe we'll do an export for that. We'll see how far we get. Okay, so this is going to be a breakout board. So a breakout board typically is just a component and a header, and it's going to be just leads that run from the component pins to the header pins. So this is a power regulator. So normally actually with a power regulator, if we're doing a breakout board, we would probably want to add more components than we're going to in this video. So power regulators, it's usually really important that you have your inductor and your diodes very close to the regulator itself. Usually they switch at high speeds. It's not good to have long capacitive and inductive lines leading to those components. It would probably work, but not as well. And if you're trying to replicate the way it's actually going to work on a board, you might as well, if you're doing a custom breakout board, also have on that breakout board at the very minimum your inductor and your capacitor for the design. We're not going to do that. Again, this video is we're just going to keep it simple, but it's just generally something you would want to do. We are going to have to do some things for this breakout board. Our component uses a thermal pad, so we are going to connect that thermal pad to a plane in order to get some, sort of get the appropriate thermal behavior out of that pad. So we have our blank schematic. Again, normally we'd fill these things in. We're not. So we're going to go to libraries, and so we already have this. We actually have two of them with the same name because I forgot to delete the old one. So this is the part we just created. If the library you just created is missing from here, and that can happen, what you have to do is you have to go here. Oops, sorry. You have to go to libraries. And then here you're going to have to install a new library. And all you do is install it from file, find where you have the library saved, and then just go from there. It's not that big of a deal. So we have our library here though. So this is the component we just created. So there's a couple things I can do. I like to right click and just go place component. And so anytime I'm working with a new schematic, I personally like to change the grid to 10. So my grid, if you look down to the bottom left corner of the screen, my grid is set to 1. I'm going to change that to 10 by pressing the G key. Press it once, You see it changes to 5. Press it again, it changes to 10. So I'm going to change it to 10 so that we get that sort of more appropriate snapping behavior. Control scroll wheel click to zoom. I'll just move up into this quadrant of our schematic. You see though the pins now snap to those grid axes. So let's place this guy here. And if we're looking at this, so this part basically has 6 pins on each side. It's got this ground pad which we'll deal with, but if we got 6 pins on each side, in addition to this component, we're going to want a 6-pin header. So we'll go to our libraries. The standard Altium library has got, under miscellaneous connectors, we can just go to header 6, and we can just use that. So we're going to place one of them over here and one of them over here. Now these particular headers, they have the pin 1 is a square pad instead of a round pad for identification. It doesn't really matter. We're probably going to label these separately anyway. But so these are the basic components we have here. One thing to note though is this component has a pad. It has a thermal pad, and that thermal pad is supposed to be tied to ground. So one thing we probably are going to want to do is actually label these ground as ground signals and connect that thermal pad to that ground signal as well. So, so we can do that now. We can just connect a ground symbol there. We'll connect another one here. And we will make some connections here. Okay. So we have all of our ground tied together, and all those are tied to that pad ground. So anytime before we migrate our schematic over to our board, we're going to have to annotate this thing. So right now, P question mark, Q question mark, etc. We're going to have to actually annotate those. So we're going to have to do tools, annotation, annotate schematics, update changes. And you see we got some nice labels here. Now we're going to go design, update PCB document, and close. And normally we should do some more checking to make sure everything was right, but this is simple enough and I'm going to ignore it. So take these components. Now, one thing to note is if we're building a breakout board, typically you want to have a breakout board something that can fit into a standard dip development board. Those have a standard 0.1 inch pin spacing, so we're going to have to be really careful when we make this board to ensure that we have 0.1 inch spacing on these headers. So to do that, I'll probably just to initially move everything into position, I'm going to press the G key, open up my grid, set my grid to 100 mil. So coarse grid at 100 mil. So I can take this guy, move it into a location, move this guy into a location, move my part, and we're going to rotate the part until we kind of see how it's trying to connect here. So it looks like that side is good, this other side is flipped. So you see I'm watching those air wires. So zoom in a little bit. If we have this part and the air wires look like that, they're all twisted over each other, it usually shows that a rotation is going to fix that up. So now a standard spine on a breadboard is going to be a 0.3 inch spacing on that standard spine. We're not going to be able to really fit our breakout board into that, so instead we'll do, I think we'll do a 0.5 inch spacing here. 1, 2, 3, 4, 5. We got a 0.5 inch spacing right now. Now we're going to move this component. It's a little bit too rough having a grid of 0.1 mil, so we're going to press the G key again. Take this guy down to 25 mil or something and move it into what seems like a reasonable position here. That looks pretty good to me. Okay, so first thing we're going to do is we are going to route these signals. So usually if we have big spaces like this, this doesn't show right now on our part. It doesn't actually have a name for these, and we didn't label any of those connections in our circuit. But on our original, if we go back to our original design here, we know that pins 1, 3, 16, 14, which are spaced out, these are going to be, at least the switch and the VN and the ground are going to be fairly high current carrying signals. It's probably good to make these have as fat of traces on these as possible. and that may be why they left us. That's maybe why they have this space on this sort of non-standard footprint. So we'll just go ahead and just do fat traces for those. So let's make sure our layer is top layer for these traces. Select interactively route connection. And that's not quite fat enough for us, so hit tab. Let's change this width to, let's do 24. Yeah. Now there's certainly better looking ways to do this. This is not normally what you'd want to do. Normally what you'd do is hit tab, change your width to something like 12, get yourself a little ways out of the pad, then switch to something bigger like a 24. So that's typically what you do. It's going to work either way in this case. It just doesn't quite look as great. Actually, neither of these look that fantastic, but they're going to work. So for these guys, obviously that thick trace doesn't work, but I think a 12 mil trace should work just fine. Yeah, 12 mil trace looks good. Now I'm hitting escape after I finish the route, and again, we have other videos where we talk about how to route these. I'm actually not going to worry about that other ground just right now. So again, we'll take this guy out a little bit, hit tab, bump it up to 24. Again, so this is not my proudest moment here. These are pretty ugly traces. But the general rule is you want to keep the copper for a breakout board, you want to just make it as fat as it can be and still not violate any of the rules. Okay, so that's looking pretty good. So now we have the other grounds. I connected this ground, and I probably didn't need to, but I have this ground connected here. What we're going to do is we're going to add a ground plane to this entire thing. So we're going to add a plane of copper which connects all these grounds, and that's going to help. That's going to meet the required thermal needs of this ground pad here. This ground pad needs to be connected to a large ground plane to get the proper cooling for the chip. So what we're going to do is again, we're top layer, that looks good. We're going to place polygon pour. The name of the polygon pour, ground works pretty good, top layer. We're going to do pour over all same net objects, remove dead copper, connected to net ground. And then we're just going to trace this around the outline of our board. The whole thing can be, and hit escape, and that places our copper there. Now, one thing to notice here is what happened is this pour has thermal relief for these pins, and it's fine to have thermal relief for the pins, but it added thermal relief for this thermal pad connection, and that's not something we want. We don't want thermal relief. The whole point of connecting this to the copper is to get thermal dissipation, to get a thermal connection between this plane and that pad. So there's a couple things we can do to change that. One thing we can do is just go into the rules and change the rules. So if we go to design rules, if we go to under the plane, we go to polygon connect style. If we, instead of doing relief connect, we do direct connect. So that is going to not do thermal relief like that. It's just going to just directly connect everything together. One thing we can do is we can also add a rule that only directly connects if, for instance, the signal is ground or something like that. So if the net is ground, and we can even do that. So the net is ground, then we can have this rule where it's going to be that. Okay, and you see it didn't change anything. We have to go back to Tools, Polygon Pores, Repour All. And after we repour all, now we got a nice looking ground plane that just, instead of having those thermal reliefs, it just does a direct connect to the pad. So, and again, the reason we normally want thermal relief is because thermal relief helps us if we're soldering by hand. If we're throwing the whole thing in an oven, it doesn't really matter. But if we're soldering by hand or trying to do rework, it can be very difficult to get enough heat on a pin to to melt the solder on that pin if that pin doesn't have thermal relief. So that's kind of what the reason we normally do thermal relief. The reason we're getting rid of it here is because we want that nice thermal conductivity. So let's do even more. Let's take this a little bit further, and let's add, just for extra little thermal relief, let's also add a ground plane on the bottom of the chip. So let's switch to bottom layer, place, polygon pour, connected to ground, pour well, same net objects, bottom layer. It's good. So same thing. Okay. So now I created this ground plane on the bottom of our board, on the bottom layer. The problem is, right now, this is not giving great thermal relief to the chip. If we want to get great thermal relief to the chip, we're going to have to thermally connect the top layer and the bottom layer.
John Lund is awesome!
John Lund needs to have a video studio. So we're going to connect those two layers together by doing place. Yep. And if we hit, so we're going to place this via and 13 mil, 27 mil, that's what our fab needs. But now we're going to say, nope, that's going to be connected to net ground. So it's going to be connected to net ground, and then let's just do there, 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 there. Perfect. So what we just did, now if we switch to the top layer, what we just did is we made a connection. I don't quite like where those are. Those are actually off the thermal pad. I didn't realize because I was on the bottom layer. So let's set our grid a little bit finer, 10 mil maybe, and move these guys in a little bit, maybe in a little bit more. There we go. Okay, that was a little bit better. All right, so let's see what this looks like in 3D now. So let's go 3D. Oh, and one thing you notice is my board is way too big. So let's go back and define the board shape here. So to define the board shape, we're going to click the 1 key. So 1 key takes us to the board shape definition. We're going to do redefine board shape. Set our grid back to 25 mil here. board shape there. Yeah, we might want to do it a little bit bigger. Let's give ourselves a little bit of space outside of here. So just redefine board shape again. Hit escape. Then we can hit the 2 key to go back here, or the 3 key to go back to the 3D view. So far it's looking pretty good. We've got a connection here. And it's looking pretty nice. So there's a couple things you might want to do. So one thing is these vias that I put here. You can see them. They have exposed copper now on the back side of the board. Sometimes that's not. Sometimes we don't like that. Sometimes we'd rather cover these up. So one thing we can do is if we go back here and select all of these. So one thing I'm going to do is I'm going to just click on one of them. Oh boy, it's hard to click on one of them sometimes. And I'm going to do find similar objects of type via, apply. So that selected all of those. And then I'm going to do solder mask tenting bottom, true. So tenting means it's going to cover that via with solder mask, and you'll see what happens if we go back to our 3D view now. If we go back to our 3D view, you see those are now covered. And so the nice thing about that is it's going to prevent that solder from sort of bubbling up on the back side of the board. Although sometimes people like it for prototyping to be able to have access to that, because it gives you a place where you can add heat to melt that. With an iron, you can add heat to melt that that thermal connection there if you need to. So whatever, it's sort of people's personal preference. Okay, so there's a couple things we need to do. So one thing is, this is a breakout board, so I always like to specify what I'm doing here. We don't have very many parts or headers. I don't think I really need the designators here. So I'm going to click this. I'm going to click the designator, and I'm going to click hide, and I'll do the same thing for these guys. There's another way to hide it, I guess, depending on what you clicked. Okay, so we're going to hide those designators. I want to have, though, on this breakout board something that tells me what device this is a breakout board for. So I know this guy is an LTC 3638. So what I'm going to do is I'm going to go back and I'm going to go to my top overlay and do place string. And hit tab and type in LTC 3639. It's a little bit too big, so I'll hit tab again, and I'll change the height to 50 mil, the width to 8. That looks a lot better. And I hit escape, by the way. You always hit escape to sort of break out of moving something or selecting something. Now I also want to label these pins here. I also want to label these, and this is where it would really have been helpful if I had labeled all of these signals in the schematic. But I don't want to go through that whole process just to be able to view it in the PCB board. So I'll just write these labels manually. So pin 1, switch, VN, FBO. So. And I'm going to hit G and change my grid here, so I'm a little bit coarser. Right, switch VN FBO. Okay. Actually, I'm just going to go through for speed and just put all these in here. We're clearly going to have to figure something out with that guy there, but we'll get to that later. So with this one, we don't have enough space for FBO, so we'll just do FB. It's good enough. The next one is V program 2. So we'll just say, we'll just call those P2 and P1. Oops. Then we have ground. Okay, let's place some text on the other side. We'll hit tab. So we are so this guy is, oops, I'm making a video, just heads up. No, it's fine. You're just permanently on the internet now. I'm gonna have to have you sign a release form now. So we'll just put these guys into position. Get the name. You're gonna move around later. Okay, so these are pad ground. Well, pad ground we actually don't have connected. Ground run OVLO. So for the overload, we'll just do OV for that. Move it over. Oops. Then I set, we'll have IS, SS, and VFB. This one was IS. This one was SS. This is VFB. Okay, let's double check that. Yep. Okay. Now what about this? Now our label that we had for this chip is now, it doesn't really fit very nicely anymore. What are we going to do with this guy? One thing we can do is just place it on the back of the board. How do we place it on the back of the board? One thing we can do is we can just select it, and we can do move, flip selection. So if you flip the selection, it's basically, if it's a component or a text label or anything, if you flip the selection, it's going to move it to the other side of the board, which means any top copper becomes bottom copper, any top overlay becomes bottom overlay, etc. It also flips it visually. So if you look at this, the text now looks backwards, but in fact, when the board is flipped over and we're looking at it, it's going to look okay, and we'll see that really soon. All right, so let's do a final check in 3D view. I don't really like that P2 is sort of crossing over here. I'm not sure that's actually going to show up correctly. Actually, these guys are sort of overlapping too. I'm not quite sure why I didn't see that. So typically, silkscreen is not going to actually write onto the silkscreen. Usually will only bond to the solder mask, so all of this stuff is going to get clipped off. There's a few things we can do to fudge this a little bit. Probably we should redesign it and just change our font size. But just to cheat a little bit, I'll probably just change these guys. So we'll switch these to 40 mil 6. And maybe give them a little budge now. Yeah, let's give those guys a little. Okay, check it again. It looks a lot better now. That's actually going to show up at least. Not perfect, not ideal. Kind of sloppy with a different size font, but we're trying to sort of move this thing along. It's usually kind of important. You don't have to necessarily see the component name from the top, but if you're breadboarding this, it's really nice to be able to see the signals that you're connecting to, so it's nice to actually have these be visible here. Alright, so it looks good in 3D view. Let's flip that around, by the way. There we go. So that LTC 3639 looks fantastic down there. It's easy to identify. Everything's looking good. Okay. So now let's export this board for fabrication. So if we're going to export this, we've done this in other videos, but we'll do it again this time. So if we are exporting this, first of all, let's save everything. We probably should have saved a while ago. It's probably good to do a design rule check. We have a silk to solder mask and a silk to silk clearance. I'm not very concerned about those, so I think we're good to go. So let's do file, fabrication outputs, Gerber files. 2 to 4 is what I like. It depends on your fab. Plot, top overlay, top paste, and we're going to flip that. Top solder, top layer, bottom solid or solder. Don't care about bottom paste. Bottom overlay. Oh, we don't have our mechanical outline yet. So, I shouldn't have done that. That's fine. Okay, so we have to still do an outline for the board. Let's just choose something we haven't used. Choose a mechanical layer. Let's do mechanical 5 in this case. Place, line. So this is just a way to specify the board outline. So we have the board outline that Altium knows about, and then we have one that's going to be exported for the fab. So now mechanical 5 represents our board outline. So now we'll go file, fabrication outputs, Gerber files, and we're going to export mechanical 5 too. Looks good. Export all that. We do file, oops, we got to go back to our board. File, fabrication outputs, Gerber files. Sorry, file, fabrication outputs, NC drill files. I like 2 to 4 is the most compatible with the fabs that I use. I like to keep leading and trailing zeros. Reference doesn't really matter, that's fine. Okay. And so now it's got all of our drill hits shown here, not too many of them for this application. Let's again do file, save all. So now we've exported all of the Camtastics, just save them as whatever. Okay, so we've exported all the files we need for fabrication. So what we can do now is we can go to, if we go to Documents, ML Studio, did we call this thing anything? What am I doing here? Sorry, Altium, jeez. Altium projects. This is Buck Breakout. Project outputs. So first thing we're going to do is take that mechanical 5 layer and just label it GKO just so they know it's sort of the board outline. Change that. And now we're going to get those 8 magical files. Bottom layer, bottom overlay, bottom silk. Keep out. Top layer, top overlay, top silk. Drill text file. Send to compressed zip folder. Call it something good. So now we have all the files we need to actually fabricate this in a nice zip folder. If we want to now, we can go to OSHPark here. So if we wanted to have this fabricated at OSHPark, we can check this. OSHPark, I think, is really good for these little types of breakout boards. Don't pay a lot for shipping. That's the biggest thing. You can get them fairly quick. So look at that. It's all ready to go. This board. We could do this. So this is saying 3 boards will cost you $1.95. It's hard to beat that for breakout boards. And so we could continue. Check, inspect everything. Everything looks good. We could buy this from OSHPark. It would get here in 2 weeks, maybe a little bit less. Costs us just a couple bucks. Typically, if it's a breakout, though, I'm going to get more than just a couple. I'm going to probably get, 9 or so. Pay $6, not a big deal. So that's one option. So that's what we could do there. The other option is we could go to, if we're doing a lot of designs and we have a lot of designs, we're trying to get them cheap. It's hard. We're not going to be able to get something this small cheaper than this. But if we want to do PCBWay, which is another common one, I use PCBWay a lot. You're going to have to eventually sign in, so you might as well create an account. Look at that. Well, this is embarrassing. Well, we'll just do it without creating an account. Apparently I'm having some account issues here. So PCB Instant Quote. So if you're using PCBWay, the one thing to note with PCBWay is you've got to know the dimensions of your component. You've got to know, you got to specify. If you're wrong about this, the estimate that they give you could be wrong. One thing you can do is you can, OSHPark, I'm just clicking the back button here. They do tell you the dimensions. So 16 by 16 millimeter. Oh boy, we weren't trying for that, and we got a perfect square there. So you can do 16 millimeter by 16 millimeter. Type in your quantity. Let's say we're getting 50 of them. We can pick our color with OSHPark. So the track spacing. You got to be careful with your design, because if your hole size is smaller than the cheap version, which is 0.3 millimeters, or if your track spacing is less than 6 mil, they will just sort of charge you extra. They'll just sort of upgrade the estimated cost for your board. So you really want to make sure that your board meets the requirements for the low cost version before doing it. So no gold fingers. So the only way to get cheap with PCBWay is to go with this Hazel surface coating, which is a lead. It's hot air solder coating of the copper. That is leaded solder. So so just be aware of that you're possibly getting lead with your prototype. And then you could go calculate, and then it'll give you an estimate. So this is $16, but that's for 50 of these boards. So pretty good cost, and usually for bigger boards, this is works better. We can go, please input email address. We'll try that one. Please join us. Yeah, so they want you to create an account and everything. It's not a big deal. Basically, once you add it to your order, it takes you to the cart screen, and it when you're at the cart screen, it's going to it's going to be, basically you're going to have to wait for an engineer at PCBWay to check your design and make sure it's all correct. So all you do is if you create an account and you log in and you add it to your cart and you upload the design, they have to actually manually check it. Each design gets manually checked, so you got to wait. You also got to keep in mind that it's different. China time is different than the time wherever you are. So you might upload this at 2 p.m. and say, oh, it should get all ready to purchase by the end of the day, but not necessarily. So just keep that in mind. They are generally a lot cheaper for big boards. They're a lot cheaper for small stuff. A lot of times OSHPark is the best way to go, though. So Okay, so that is the process, though. That is the process of creating a breakout board. And from start to finish, the previous video to this video is the complete process of creating a breakout board, designing it, and sending it off to fab. So I hope this helped you. I hope you can follow through and use this as a tutorial to create your own breakout boards, and also do them quick. So have your breakout boards. If you're doing the senior design project, you're going to want those breakout boards as soon as possible, so that you can start your prototyping. So